What I'm planning to do, as I said, is I'm going to do the CSPs and SAT problems as the main topic. But before I go there, I want to spend a couple of minutes talking about conditional planning with respect to propositional belief states. That I became very close to. You read the paper and you just didn't discuss this, so I wanted to just sort of do it once in the class for a couple of minutes so that you know that you need to remember that. Okay, so it's kind of useful to think of a progression planner in the space of belief states, essentially as the following simple procedure. So you're starting, you've been given some goal, and you have a current plan and you have a current belief state. Now, if the goal is satisfied in the current belief state, because you are going progression, okay? So if the goal is satisfied in the current belief state, then you're done, you just return the plan. Okay? If not, then you get to do basically search. And the search is two different parts. One is you can non-deterministically choose. So first of all, we differentiate between actions that change the world and actions that only sense the world. Okay, so the observational actions and causative actions. Okay, all the actions you have known until now are those that change the world normally, except the ones that we talked about, as part of POMDB, which is observation actions. And actually, what is kind of interesting is in real world, actions have both observational and causative effects. Okay, so we will for now actually avoid thinking about that. So we'll act as if there are pure observational actions and pure causative actions. Okay, so you can of course do, basically you need to consider, you're doing progression, you're considering doing actions from the current state. Okay, you have to consider doing each one of the actions for completeness sake. Okay, so that's why this is a non-deterministic choice, and what that means is during actual search, you need to use heuristics to figure out which action to use. Okay, so you would select a causative action that is applicable to B, and then actually apply that to compute the new belief state. That's one idea. The other idea is non-deterministically select a sensing action and do that sensing action. And what the sensing action does is it takes the belief state and splits it, partitions it into the part of the belief state where what the sensing action senses is true and the other part where it is false. So the simplest kind of sensing actions are sense the value of a proposition, state variable. Okay? So if I say observe P, then essentially my belief state suddenly gets split into old belief state plus P and P, and old belief state and not P. And those are two different belief states now. So suddenly actually the search has split into a fork. And so you need to consider doing and or search there. Okay? The point I was trying to make is you get to decide whether to select a causative or an observational action. Okay, and one of the useful things is if you decide never to pick an observational action and you still solve the problem, then essentially you did conformant planning. You did nonsense planning, no sensing planning. Okay, right? And if you also allowed to do this, then you did, basically conditional planning. You can also say, what if I choose never to do causative action? That's, I guess, what's that new movie, the Perks of Being a Wallflower. Okay, so you just basically get to see the world. You don't actually change the world at all. So if the world is already in the state you wanted it to be in, maybe you are done. Otherwise, you cannot actually solve any problem. Okay, so if you just do this, you solve fewer problems than actually are solvable. If you just do this, even fewer problems. If you do both of them, then you're essentially considering conditional planning. Okay? And after doing that, essentially, then you get the, you recursively call this once more. That's basically what you're doing. And two simple examples I want to discuss. One example where A1 is a causative action, and it basically says, remember, we are going to add act as if there are no preconditions. So A1 says if whenever P is true, it makes R and not P. Okay, and A2 says whenever not P is true, it gives R and P. And A3 says whenever R is true, it gives G. And then there is an observation action called O5, which all it does is observes P. That's all. It's a very simple example. Okay, so if I start from here, and the first thing, and I'm actually not going to draw the entire search diagram, I'm just going to show one trace that gets you to a plan for this problem. Okay, so suppose I were to do O5, which will be in the search space, right? You're considering non-deterministic choices. So if you were to do O5, then after O5, so in the initial state, essentially let's assume that we don't know at all anything as to what the current state is. Okay, what that essentially means is initial state is true. Okay, that means you have actually, every one of the possible assignments is still possible. It's a big disjunction. Okay, so and then after O5, then either you have P true or not P true. Because O5 would tell, basically observes P, right? And so this is still in the thinking time. So you would either have a belief state where P is true and a belief state where not P is true. And which is which? Because O5 tells you at the runtime. Okay. Now you need to take both of these to go. Okay. So now from here, if I do A1, I would get R and not P. That's what it says. And if I then do A3, then I get G, R, not P, which is a goal, because that satisfies the goal condition. Similarly, here if I do A2, I get R and P, and if I do A3, I get G, R, and P, which is again a goal. So I satisfy the goal condition there too. So since every leaf node of this plan, this tree is a solution, the tree itself is the conditional plan. Instead of a sequential plan, you have a tree-shaped plan, which is a conditional plan, right? Okay. Now, in fact, in this example, you can get a conformant plan too. It turns out. So if you chose to not try at all any sensing actions, okay, then you could, for example, show to yourself that if you were to do A1 and then do A2 and then do A3, you'll get a single belief state where G is true. So this is what I was saying. Sometimes for a given problem, there are both conditional and conformant plans. As to which one you will pick depends on your costs. For example, if the conditional plan is costly, if the sensing is costly, then you might go with, without sensing. You see what I'm saying? Okay, but it will never be the case. It can be the case that there is there's a conditional plan but no conformant plan. Okay, that's possible because there may be problems that cannot actually be solved without sensing. Okay, so one more slightly more complex example, which is actually a nice example to keep in mind, is this Medicaid example where without sensing there is no conformant plan. Okay, so without sensing there is no plan. So here the idea is that, basically if you give the medicine to a patient who is not suffering from the disease, then the patient will die. But unfortunately, you don't know upfront whether the patient is suffering from a disease or not, because disease is not observable. However, there is a test which will say one thing if the patient has the disease and another thing if the patient doesn't have a disease. So then you will do the test only to figure out whether the patient has a disease or not, and if the patient does have the disease, then you medicate the patient. If not, you don't medicate the patient. That's the basic idea of Medicaid problem. So here is a very simple formalization of it. Here it says the patient is not dead in the beginning and may be ill. So that means the initial state is not D and I are not I. Ill being the state variable for disease. Right? So that, and furthermore, the test paper in the beginning is not blue. Is a test paper that's not blue. Now we want to make a patient be not dead and not ill. Okay, that's our goal. Okay, and we have 3 actions: medicate, which makes the patient not ill if he is ill. So that's medicate. Not ill implies not ill. Not ill implies dead. Right? That's the action. It's a reasonable thing. Sometimes medicines can kill you. Okay. And then that's the medicate action. M, there is a stain action which makes the test paper blue if the patient is ill. It's some sort of a medical test. Okay. So the stain action, if you do this, the paper will stain blue if in fact the patient was ill to begin with. If not, it won't change the paper. And there is a sense paper action which actually senses the color of the paper. Right? That's the basic idea. That's how tests are done. If you think about it, people will do something, they'll make you drink, some glowing iodine solution, and then they will take an X-ray of you, and it will be very colorful. And then they'll laugh at you, and then take you money. Okay. But anyway, so when they made you drink this glowing iodine solution, that's a causative action. It's just flowing through your body. And then when they switched on the X-ray or etc. is when they are sensing what is happening to you. Okay. So this is a causative action which almost doesn't seem to have any connection to what you want to do. It's only connected to what you want to sense. And the sensing is important because otherwise you might kill the person before curing them. This is the kind of thing that happens in conditional planning. Okay. Now, one of the interesting things you could probably see from my discussion itself that it becomes hard to talk about goal-directedness in your reasoning. Okay, what are you trying to do? You're trying to make sure that the person is cured. So why are you then staining papers? What is the connection? Do you see what I'm saying? So if you go from the goal towards the initial state, it's not at all obvious that staining the paper is worthwhile action to do. Now when you're going forward, of course, you'll try everything. If you try this too, then you will be complete. So the heuristics for conditional planning have to be, that was that paper, the rest of that huge paper that the first piece of which we read, that one essentially considers this whole issue of, how do you come up with heuristics, both in conformant and conditional planning scenarios. And especially in conditional planning scenarios, the issue is, how do you even tell that by doing a sensing action, you came closer to the goal? Because it doesn't do anything, it just changes your head. So how can the state be any closer to the goal? Which is what normally heuristics are supposed to do, right? Okay, so anyway, let's do the, forward direction, the progression. So I have my belief state. This is in the DNF form. Okay, so this is not dead, ill, and not blue, and not dead, and not ill, and not blue. These are the 2 possible states. In fact, this is a logical formula is what I have in mind, really. There could be other variables and I don't care about them. That's the point. Okay. Now, I do stain. I can do it. So I do stain. And then what happens is, in the scenario, in the belief state where ill is true, it makes it blue. In the other scenario, it just leaves it alone. So that's the cute part of these tests. You don't know, but they know. The tests know, right? So the stain basically what it did is this variable is interestingly observable. B is an observable variable, right? Because you have an action which observes that variable. There is no observation action that tells you whether you are ill or not. So by the way, that also means this is a problem that is partially observable. You don't get to observe every possible variable. Okay, so part of the whole tests are to convert what is not observable into what is observable, and then you observe it. Right? Okay, so then you got this. Now if I do my sensing action, which is sense paper, then that will split this into not D, I, and B, and not D, not I, and not B. Now here, you know that this will be split, so sensing paper will either give you, it is blue or it is not blue. That's what it will tell you, okay? It is not blue branch, you are done. You're done. Right? Because all you wanted was the patient is not dead and not ill. Not dead and not ill. You're done. It's not because of the not blueness that you are done, but it's because of the not deadness and not illness. But not blueness gets attached to that. Right? Okay. On this side, on the other hand, you have not dead, ill, and blue. Okay. Now, if I do the medicate action, this medicate action, which basically only this part will work because the not I part won't work because there is no not I here. Okay, so the medicate part will give me not D, not I, and B, which is again a goal state. Because you're not dead and you're not ill. So I'm stuck here. So that's my plan now. Okay, so the plan is one action, an observation action, and then one branch anyway stops, another branch you need one more action, and then you do it. Again a tree-shaped plan. Okay, so that's basically, it's a nice partially observable scenario, and it also kind of brings up the kind of the interesting aspects of conditional action, the observational actions. You know, observational actions and their cohorts, such as the stain. With stain is basically converting a non-observable variables into an observable variable. Basically, the observable variable is correlating with the non-observable variable. And then the sensing is done on this observable variable. Okay, so in progression, you don't ask, are you goal directed? But, you know, as I was mentioning, consider going in the regression form. Remember, every time we talked about progression, we also talked about regression in the past. Okay, and I would not like to do it for this problem for the reasons that become clear to you. Because regression doesn't look like regression anymore. You know, because, so consider the following thing. So, this is the progression tree. This is for the simple problem. I'm only doing a simple problem. And this is the progression tree. First one, right? Now, if I'm doing the backward way, which is the regression way, so I start with G, okay, and that's what I want, and then I can regress, you know, A3 over G, and then I will need R. Right? Okay. In fact, I should say RRG from what I told you last time. But you know, let's just write R right now. Okay. And then at this point, if from R I can do A1, I can get P. Okay, because over A1, A1 will give me R. A1 will give me R. Right? But it requires P to be true before. Okay, and then A2 will also give me R and requires not P before. And the problem is you have to try both of these because you don't actually know what is the value of P here because you're regressing anyway. Okay, now once you got this P and not P, you need to combine them. You need to do this reverse operation. You have to combine these belief states into a single belief state. And you can do that by regressing the P and not P belief states over the observational action 05, which collapses them. Which intuitively makes kind of almost no sense because do we wait for S2 and S3 to come into being before you then put in the A05 and collapse them? Okay, so you can almost see that this part is goal directed. Or any one of those branches is goal directed. But what is this other branch coming? Where are you getting it from? So in essence, that's the conditioning branch. And the conditioning has no real goal directiveness. It's just essentially saying, I have to condition it on the observable variable B. Okay, and that's why regression becomes more complicated. I'm not I'm just giving you kind of an example of the kinds of issues involved. And this was the regression version for the Medicaid problem. Okay, but in general, when you have sensing actions, regression is more complicated. Yes.
Can you go back to
yes.
the previous
Yeah.
one? Can we treat this like the regression as like this like kind of divide the goal into some sub goals, like the G.
Yeah, except you are now collapsing them. You're collapsing them. So that is the point. So what happened here is the reverse reduction. I mean, because normally you would go from a problem into sub-problems. So if you look at this direction, that has the and/or feeling to it, right? Because you start from a single belief state, now you have to make sure that both these belief states go home. Here you're doing the reverse and/or operation. You're taking two belief states and collapsing them into one belief state after the observational action. Okay? I'm mostly just trying to bring that up. I think I only want you to understand the progression part and the part that you actually do have a choice as to whether you try both causative and conditional actions and observational actions. And if you only do causative, then you get conformant. If you only do observational, then you get a purely observational plan. Okay, and then if you do both, then you get normal conditional plans. Now, one thing that this is just the scratching, this whole discussion is scratching the surface of conditional planning. Because in general, one of the interesting issues is, once you start having observational actions, your goals also are richer, right? In classical planning, for example, okay, I might have a goal of making sure that a particular person is not going to fall asleep. That's my goal. So I'll keep singing at the top of my voice, and then they'll stay awake. So I made sure that they're staying awake. That's the only goal I can have in classical planning. But now that I have observational plus classical planning, I might say, check if your dad is awake. Right? Now, what is the semantics of a correct plan for checking that? Do you see what I'm saying? You go into the room and say, Dad, are you awake? And then he would be awake, and but you didn't check it. Okay, do you see what I'm saying? So how do you make sure that check if, there are goals such as check if this guy is having the following disease. Well, I can give the disease to the guy and say yes. Right? Okay? And so the point I'm trying to make is that in, this you can read this, I'm not going to go through this, but there are a whole bunch of things that we pushed under the rug. Once you start having observational actions, and once you start talking about goals in propositional forms, there are all sorts of interesting goals you can talk about, for example. And then supporting them becomes a much more interesting operation than just reaching a state where those things are satisfied. Because find if actions are not allowed to change the state and say, look, it is true. Do you see what I'm saying? Okay, and that becomes an interesting semantics issue. So I'll stop there on that one. Any questions on this before I move on to CSPs? So, as I think we kind of went way in complexity, and now we're going to fall down and then slowly go way up complexity. Right? CSP is really taught in intro to AI. Okay, I'm bringing that up because I want you to know some of the ideas there, and then we'll use them as we again ramp up. Okay, so CSPs are very simple problems. Again, we are now in the propositional, or we're not in the atomic states, we are in propositional states. Okay, so basically in CSP, and I'll go through this relatively fast because really it's a much simpler idea, and then you should be able to read the chapter. Okay. So you have a set of state variables. A state is defined in terms of state variables. Okay. And basically, each of these state variables need to be given assignments. The variables have, possible values, the domain from which they can take their values, and you need to give them assignments. And then when you give every variable an assignment, then you're done. You solve the problem. Okay. The only tricky part is there are constraints. The constraints essentially saying certain partial assignments are not allowed. Okay, that is, if x has value a, then y cannot have value b or c. Or x has value d, then y must have value m. Things like that. Okay, constraints, as we'll see in a minute, essentially are basically saying what are either legal partial assignments or illegal partial assignments. Any which you can either think only in terms of legality, and so then I give my partial assignment to the constraint and it says, yes, you're still legal. And then equivalently I can think of my constraints essentially telling me what is no good. In fact, the word no good is a no good. Okay. So a constraint can be a no good, which means that if your big assignment ever has x equal to a and y equal to b, it's no good. So that means the entire partial assignment is dead now. You see what I'm saying? So you can think of constraints either in terms of legality or illegal. Any which way, either way is fine. Okay. So given these constraints, then the objective is just to find a solution. A solution, not even the best solution right now. There is no such thing as best solution. Any complete assignment of values to variables is a solution. What's interesting is this very simple problem, first of all, has all sorts of uses and all sorts of deep connections to lots and lots of other things in the world, and plus it has all sorts of interesting extensions. And of course, as you can see right away, I could say, find me the assignment that is the best in some sense. Okay, and then to be able to say the best, I might, for example, say, well, here's a constraint, if you violate it, you get this much penalty. It's not that you're not allowed to violate it. If you violate it, you'll get this much penalty. Then tell me, give me an assignment that has the lowest penalty. So if an assignment basically satisfies all the constraints, then it has 0 penalty, so it's the best. But many scenarios you might have constraints that are essentially not possible to satisfy altogether, and so you have to pick. And then that would be the max CSP, okay, or soft CSP. Okay, so there are all these nice extensions are there. Okay, so it's basically from a very simple search point of view, the goal state is any state which has all the variables have assignments and none of the constraints are violated. That's it. Okay. Now, of course, one of the nice things is why not you just do it brute force way? If you have n variables and if the maximum domain size of any of these variables is d, right? Then the total number of assignments, complete assignments, is d power n. Okay. Now the question is whether or not the CSP is easy or hard to solve depends essentially on how many assignments actually satisfy all the constraints. For now, again, I would assume that I'm only interested in finding assignments that satisfy all the constraints. So given a CSP, either you solve it by giving me an assignment that satisfies all the constraints, or you say, I'm sorry, it can't be done. In which case, I will take you on your word. If I can actually find an assignment that does satisfy all the constraints, then you are not a sound algorithm. See what I'm saying? Okay? So anyway, so since there are d power n assignments, then essentially it's an exponential. In the brute, at least the brute force way is exponential. Okay. What is interesting is general CSPs are in fact, just saying that brute force is exponential doesn't mean that there is no efficient algorithm, right? But general CSPs are indeed NP complete. Why is that so? Why is that so? Because a special class of CSP is SAT. SAT is a CSP where there are n Boolean variables. Boolean variables. So that means there will be 2 power n complete assignments. Now you all heard of, if you are in CS, you have heard of satisfiability problem, right? So if I give you a set of Boolean variables and a set of constraints on the Boolean variables. Now in SAT, how do you write the constraints? I write constraints like this. I might say P, Q, R are my Boolean variables, and my constraints are P implies Q and R are not Q. Those are my constraints. Basically, you will write the constraints as SAT propositional formulae that must be satisfied by any complete assignment that you say is a solution. Okay? And in fact, going one step forward, it turns out that if you have any of these kinds of things, you can convert them into CNF representation. CNF classes, right? Because any arbitrary Boolean formula can be converted into CNF classes. And so you can have a clausal representation of the constraints, where a clause essentially is of the form. So for example, this will become the clause not P or Q. That's the clause. So basically you just write not P, comma Q. Okay? And this will become just the clause R, comma not Q. R, comma. Okay? The funny thing is, this computer is much faster in booting up, but it's extremely, has very high latency when I'm writing on it. So, I have a hard time writing on it. But anyway, so that's your, set of classes. A SAT problem essentially is a set of Boolean variables and a set of classes, and finally the satisfying assignment. That's what it is. Now that's the canonical NP-complete problem. Stephen Cook, in 70s has shown that any other class NP problem can be reduced to Boolean satisfiability problem. Okay, in a polynomial time. And so, if Boolean satisfiability can be solved in polynomial time, so can all these class NP problems. That's basically what he showed, right? And so, Boolean satisfiability is the canonical, the very first NP-complete problem. And so, since CSP is the general case, SAT is a special case of CSP, CSP is also NP-complete in the worst case. Okay. But we will look for special scenarios where CSPs are actually easy. That's part of what we'll do. Okay. Tractable subclasses. Okay. So here is an example, coloring problem, is an example. You have 3 regions and you need to color. The CSP representation, you need the variables, those are the variables. You need the values for the variables, red, blue are the values, and you need the constraints, and the constraints essentially are saying, this guy cannot have the same value, this guy cannot have the same value, this guy cannot have the same value. Now, how do you write this? As I said, you can write it any which way. In fact, I would say you can write it either in terms of legal assignments, legal partial assignments. Okay, so I might say the constraint xy is red green or red blue or green red or green red or green blue or blue red or blue green. And you have to pay attention and realize that I did not allow red and green, right? So those are the only allowed assignments. So I could do it that way. Or I could go the opposite way and say this constraint is red, not allowed. Red, green, blue are no goods. Okay? A third idea idea, which actually is also allowed, and we'll see in a minute, is a constraint. Actually, all the CSP algorithms are written and developed in such a way that all they care about is there exists a piece of code which takes the partial assignment and says legal or illegal. That's all. They could care less as to how, in fact, the constraint is represented inside. In fact, it turns out CSP versus SAT, this is a big difference. General CSP algorithms assume that constraints are just pieces of code, which will give true false. Okay, whereas SAT, on the other hand, assumes that they are written in declarative fashion as clauses. And in fact, that also means that sometimes SAT algorithms might run out of memory before they even start solving the problem, because they have to write all these clauses. Do you see what I'm saying? Okay. Imagine you have x and y are numbers between, integers between 1 and a million. And you are saying x should be, x minus y should be less than 7. Imagine writing this as actual, as a normal set of legal or illegal assignments. That will be just too large. Whereas you can just do that as an arithmetic constraint, and and that thing just tells you yes or no, looking at the assignment, and be much simpler. Okay, so there are advantages for declarative versus procedural representation. For now, we'll assume if that basically the conceptual representation is they're telling you the legal assignments and the legal partial assignments. Okay. And one of the interesting things is actually you can think also of something called a constraint graph, which is a graph made up of vertices which correspond to the variables in the CSP, and there is an edge between the variables if there is a constraint connecting them. Okay. So in this particular problem, of course, all the constraints are actually binary constraints, right? And because of which, actually, the graph is a real graph. If you have ternary constraints or KRE constraints, then you will have hypergraphs. You have variables will be the vertices, edges would be hyper edges. Since people don't like hypergraphs, okay, and since any CSP problem that has non-binary constraints, it turns out, can be compiled down to a CSP problem that only has binary constraints, with only a polynomial increase in the size of the problem. So entire CSP literature just blithely assumes that the only interesting constraints are binary constraints. They do realize that there are non-binary constraints and they'll make amends for it, but all the theory typically assumes binary constraints. You get that? Okay? Okay, so, and then you have to do some algorithm on finding essentially an assignment that will work. Okay, and the algorithms essentially, there are multiple types of algorithms, but the one that we look at is a backtracking algorithm, and then usually talk about the heuristics for improving the efficiency of the backtracking algorithm. Okay. The other interesting thing we'll see is search basically tries to look for an assignment that will work. And one of the things that we'll find is we'll talk about why do CSP problems become hard to solve to begin with. And we'll realize that it has something to do with essentially how tightly specified the CSP problem is. And we talk about these notions of K consistency. Okay. So basically the idea is backtracking is hard only if you have to. Backtracking algorithms are hard only if you have to. Yes. Backtracking is easy if you don't have to backtrack. Why do you have to backtrack? Because the assignment that you gave to some variable somehow winds up not being happy with any assignment you can give to later variables. So you have to come all the way and change this guy's assignment. You can ask yourself, why is that so? Why can't everybody get along Why can't people be consistent so that the value they take is taken in such a way that everybody that comes below them will still have a value left for the value that they have. Do you understand what I'm saying? Okay, so for example, then basically then there is a way that you will never have to backtrack. So for example, if I'm trying to set up my office hours, and if I say it's 12 a.m. in the night, 12 midnight and in Flagstaff, right? Okay, right. The chance that I will have to backtrack is very high. Okay, and so I try to pick something which will actually have leave you some possibilities. You see what I'm saying? So that's again this notions of consistency that we talk about. And in the context of CSP, those of you who may have heard of CSP, you may have heard of things like constraint propagation and arc consistency, and those are essentially the different statements. We look at this one. Okay? So of course the solution here would be that 20 in this case. Okay, this I already mentioned, that representing a simple constraint like x is not equal to y can be written either in terms of legal partial assignments, can be written in terms of illegal partial assignments, which will be called no goods. Okay, so suppose I have this assignment contains a no good because RR is a no good, so I say it's dead. Okay, in fact the nice thing about no good is if you are violating, if you wind up having at least one of the no goods as part of your current partial assignment, then you're dead. Okay, another thing is during search, if a partial assignment is dead, it will never become undead. Because it's backtracking search, so you pick variables and keep giving values to them. More and more variables will be given values. Okay, so you'll never remove a value for a variable unless you backtrack. So if you're at a particular node and it already is if the partial assignment is already dead, there is no point in going forward. You just backtrack. Right? So that's the thing. And the third thing that I mentioned is, of course, the constraints themselves can be just pieces of code, opaque pieces of code. As far as the algorithms for CSP are concerned, they typically are written in such a way that you just make calls to the constraints. That's all. Okay. Certain kinds of CSP algorithms, such as SAT, as I mentioned, assume that the constraints are actually written in declarative fashion. So they have some additional advantages because everything is declarative fashion, but they have some additional disadvantages because they have everything written in declarative fashion, because the declarative fashion can be very, very large constraint. Okay. Okay, so here are some examples of CSP. There are all sorts of examples, but these are some toy examples. One is the coloring example. This is another coloring example. Okay. This one is a cryptarithmetic problem where you're trying to give a value to each of the letters such that they actually add up to the particular sum. Okay. And then this is your n-queen problem where you're trying to put n queens on a board such that no pair of queens actually going to conflict. Okay. We'll see more real problems in a minute. One of the other things that is actually very important for CSPs is many problems that you think have no connection to CSP can still be converted into CSP. For example, finding a plan of length k. So here, for example, finding plans can be converted into CSP problems. If I said that, you should be worried because you said planning is p-space complete and CSP is only NP complete. So you can't easily do, you can't do this. Whenever people say compile, they assume polynomial time increase at most in size, right? Otherwise, it's not reasonable. Now, finding an entire plan, finding a plan cannot be directly compiled into CSP with polynomial increase because plans can be exponentially large to begin with. However, I can compile the bounded length planning problem. That is, find me a plan that is of length 15 or less for this problem. That can be converted into a CSP or a SAT problem. And in fact, they turn out to be pretty fast ways of solving planning problems. And one of the interesting reasons why you should be, paying attention to this is by finding, best plans by compiling bounded length planning into SAT or CSP is no longer the state-of-the-art approaches. Whenever you have a new kind of planning problem, for example, confinement planning problem, you either get to write a new planner that solves the confinement planning problems, or you say to heck with it, I'll convert the confinement planning problem into a CSP problem. And my friend has a CSP solver. Okay, so that's basically what people do. In fact, confinement planning can be converted into CSP, conditional planning can be converted into CSP, many problems, diagnosis can be converted into CSP. So lots and lots of problems can be just converted into CSP. Okay, and so that's another reason why people pay a lot of attention to that. Okay, so as I said, there is this notion of constraint graph. So for this particular problem, right, the coloring the territories of Australia. Now notice that there is a territory of Australia which is Tasmania, where the devil exists, the Tasmanian devil, but that is far away from the mainland. And so one of the nice things is, if you look at the constraint graph, this thing is an independent subcomponent. In general, those are the kind of graphs that you like. What's the best kind of a graph for a CSP? Best kind of constraint graph for a CSP problem with n variables.
Oh, constraints.
N subcomponents.
No edges.
If no edges, that's the best. Right? So, in fact, understanding the graph topology of the constraint graph winds up being very useful. Part of the reason I actually decided to do this is also because we want to understand some notions of constraint graphs related to constraint graphs, such as the induced tree width, which wind up having nice connections to the complexity of actually solving the CSP problem. Okay, it turns out that I know that in the worst case CSP problems are exponential, they are NP complete, but there are examples where CSP problems can be polynomial. In fact, I said SAT is a CSP, right? Now, there is a kind of CSP called binary CSP, which means all constraints are between exactly two variables. There's a kind of constraint CSP called Boolean CSP, where each variable has exactly two values, true, false. Now I want to talk about Boolean binary CSP. How hard is Boolean binary CSP to solve? It's polynomial, because it also is called two-set. Right? Boolean binary CSP is two-set. That means constraints are exactly between two variables. Okay, and that's polynomial. So you know that there is subclasses of CSP which are polynomial. Okay, and so of course what's more interesting is, that's a very syntactic subclass. But what's more interesting is we can actually understand this notion of, if we understand this notion of induced tree width, then we know that it will only be exponential in the induced tree width. So even if the size of the problem is 10,000 variables, if its induced tree width is only 7, then it's only going to be exponential in induced tree. Not n power, but yes.
Is it not possible that we can pull down all the Boolean CSPs to binary Boolean CSP?
You can, but you will then increase the size exponentially. Okay, anything can be converted into anything, right? It's just the question is how much are you? You never consider allowing. You don't consider, compilations which will exponentially increase the size. And those are not good compilations. You can still do it, but those are not good compilations. Okay. So then this one is actually corresponding to three-way state, three CSP, a CSP where there are three array constraints. So between constraint XYZ, ZWR, and XZW, and that winds up being a hypergraph, where the edge is, whenever a set of vertices are in a circle, that means that's an edge between them, essentially. So those are the hypergraphs. And normal CSPs have hypergraphs as their constraint graphs. Binary CSPs have binary CSPs have normal graphs as their constraint graphs. Okay. Now the varieties of constraints, these are some terminology that you should have in mind. There is unary constraint, which means it's a constraint only on this particular variable. So X can never be read. That's a unary constraint. It only bothers that variable, nobody else. Okay. Binary constraint means the constraint is between exactly two variables. And higher order or n-ary constraint means the constraint is between n variables where n is greater than 2. And a particular class of higher order constraints are called global constraints, where those are constraints that combine all the variables. All the variables. Okay? In particular, for example, by the way, one other problem that can also be written as a CSP problem is Sudoku. Right? And in Sudoku, in each the square, right, you need to get these numbers 1 to 9 such that everybody has a different number. Right? That's an all different constraint. In fact, a particular kind of global constraint that people are, CSP would care a lot about is all different constraint. Okay? If you have n variables and they all must have different values, then that's an all different constraint. Okay. So that's kind of another higher order constraints. And then there are preferences, which are sort of soft constraints, where you can think of all these hard constraints or constraints with penalty infinity. That means if you violate them, you're dead. A preference is a constraint that has a penalty that is non-infinity. So you can blow that constraint and you just get that penalty. The question then is, what is the assignment that you can do with the lowest amount of penalty? Okay, so clearly, you can see all sorts of uses, right? For example, you have 18 different homeworks to be done by next Monday, and you also basically want to live, and thankfully some of them are hard constraints. You don't give it by Monday, you're dead. So you'll just get 0 on that homework, okay? And whereas some will say 10% penalty per day, right? Then you figure out, you do meta reasoning, and then you decide, okay, I'll work on these now and these later, and then these I plan to be late. That's deliberate being late, okay? And that's because that's the best assignment of my days of work to my jobs, such that I will get the lowest amount of penalty. Obviously, if you can get 0 penalty, it's good, but if you're not, this is the best you can do, okay? So those would be weighted CSPs. The names for that part is weighted CSP or SAT. And then is a version of weighted SAT is also called max SAT. That is find, basically in the max SAT, I don't give weights to the constraints. Assume that all of them actually have 1 as a weight as a constraint. Okay? The penalty is 1, and then the best assignment would be the one that would violate the least number of constraints, because all constraints are created equal. So max SAT is a weighted CSP where all the penalties are uniform. Okay? That would change the problem. We left ourselves, we'll just be mostly thinking of CSPs with hard constraints, no soft constraints. Okay. And then there are varieties of CSPs. Actually, I'll skip that slide up because I have my own versions of that. Here are some examples of real-world CSP problems: timetabling, job shop scheduling. If you're talking about toys, toy problems, Sudoku, crossword puzzles can be written as CSP solving. Of course, Boolean satisfiability itself is a CSP. It's a special case of CSP. And then this is the part that I'm really interested in, because that's the reason I'm actually doing this problem for you. Okay? Because many other problems can be written down into CSP problems. Okay? And it turns out that, in fact, the second best way of solving most problems is by converting them into CSP. In the old days, the reason I say this is, the old days when neural networks were the big fad, people used to say that the second best way of solving any problem is to write it as a neural network problem. And then somebody else then said the third best way is to write them as the genetic algorithms problem. And for reasoning problems, actually, if you don't have the time to come up with a specialized method just for that, writing it down and writing down the set of constraints that a solution has to satisfy, and then solving it as a CSP problem turns out actually to be a pretty good approach. And what's interesting is, since there are people whose only interest in life is solving CSP problems, okay, they don't care about planning, they don't care about diagnosis, they don't care about circuit verification, they don't care about anything else. They just want to solve CSP problems. Okay, so they have a hammer ready, and they are improving that hammer every year. So if you convert your problem into CSP, they'll solve it. And this is like the risk architecture. Remember in the old days, I mentioned this again in the beginning of the semester, you could either have highly micro-programmed architectures that support a specific problem. You might wind up doing it, in fact, if that particular problem is so important. Like, for example, there is graphics processors. There are speech processors. But the first time you write a speech recognition algorithm, you're not going to say, first let me make the speech processor for my algorithm. That way you'll never do another algorithm, another idea. Right? So you would do it on a normal general purpose computer. Okay. So similarly, in the architecture community, there used to be micro-programming, where come up with specialized architectures versus just RISC architecture, where keep the number of instruction set very simple. And then, of course, some problems might get compiled into bigger pieces of assembly code. However, because there are people in the world whose only life is to come up with better and better and faster processors for these RISC architectures, you're fine. What you could have saved by writing your own micro-programmed architecture is not going to keep up with what these guys are going to do, because this is all they do in their life. Okay. Now, having said that, actually, I have to mention. Keep this in the back of mind, that there are people in CSP community, of course, whose only interest is to solve CSP problems more and more efficiently. And that's why we can convert our problem into their problem and they'll solve it. Okay. So complexity of CSP, Boolean satisfiability is a special case, as I mentioned, of CSP problem, discrete CSP problem, so CSPs can be complete. Specific types of CSP may well be tractable. So as I said, Boolean binary is too sad, and so it is tractable. But we are also looking for other kinds of things. So one particular kind of problem which doesn't depend upon things like this, for example, if I were to tell you that the constraint graph for this problem is a set of disconnected nodes, all n vertices are disconnected, that means they're independent components. You know upfront that even though it still has d power n assignments, any assignment would work. Any assignment would work. So solving it is essentially order 1. You see what I'm saying? I mean, it's linear in the number of variables, because you have to give each variable a value. So it's not order 1, but it's linear in the number of variables. Do you see what I'm saying? Okay. Now, what's more interesting is actually that if the topology of the constraint graph turns out to be either a chain, that means, or a singly connected tree. Okay, they call it multi-tree, but essentially, all that is you have things like this. That is a, if I just have you would have seen this as a tree already, right? That's a tree. It turns out this is also a tree. It's a multi-tree. Okay? If your constraint graph is a multi-tree, or what is also called a singly connected network, then it's guaranteed that you can solve this problem in polynomial time. If you are solving it in exponential time, it's not beyond you. You can come up with exponential algorithms for sorting, right? Anybody can do anything. But you should at least hit yourself on the back of the head and say, look, people have already proved this to be polynomial. So there must be an easier way to do it. Okay. People remember the connection to the Bayes networks from the 471 community? Bayes network inference is polynomial exactly when Bayes network is singly connected. What's Bayes network? It's a constraint graph. 4 probabilistic variables. And in fact, that's yet another reason why you should understand CSP. Because the CSP people are very good at writing algorithms. And they have developed some of the better algorithms, better exact algorithms for probabilistic reasoning. Some of the people who are the best researchers in coming up with CSP algorithms also are the best researchers in coming up with Bayes network exact algorithms. Okay, for example, Rina Dechter, who basically wrote a textbook on constraint satisfaction, one of the more recent textbooks on constraint satisfaction, she completely works now in exact inference over Bayes networks. Okay, because the ideas for them are at a certain level of abstraction, they are the same. So ideas carry over. Okay, induced tree width winds up being a very important aspect of Bayes networks too. Okay, so tell me what would be the induced tree width of singly connected networks? I didn't define it at all. I was just looking at something, game theory book, where they said, suppose you have a GMAT question where we forgot what the question was. The answers are the following 5. Which one would be the correct answer? And it turns out that if you think about what the other person might be thinking in coming up with this question, you will have a pretty good chance of narrowing down what should be the answer without even knowing what the question is. That's the part about game theory, right? Now, so my point is, I didn't tell you anything about the definition of induced tree width, but I did tell you something useful about it. And I told you one other part about this particular singly connected networks. They are polynomial. So, what is the induced tree width? Yes?
1.
Yes. Because only 1 power k is 1.
My master's was in tree width. So
What? In what?
in tree width.
Tree width. Oh, okay. So there you go. So you should give us a lecture, actually. Okay. But in this case, I didn't even expect you to know the definition. It's just it has to be 1 because I said it's exponential in the tree width instead of the number of variables. Right? So and I also am saying this is polynomial. So put 2 and 2 together. Okay. So that's all these reasons why CSPs are interesting. When CSPs are introduced in the chapter 4 or 3 or whatever in the intro to AI, they don't make all these connections because they're going in the forward direction. We are going in the backward direction. We know a lot more, hopefully, about AI. And then so we can actually see, and yet we got back to CSPs, and there are all these other reasons, apart from the reasons that they were doing. Okay. Okay, so a couple of things before we leave. One of the things is CSP versus SAT, I already mentioned, but something worth saying here. Okay, so CSP allows multi-valued variables, okay, discrete multi-valued variables, and then while SAT focuses on the Boolean variables. Okay, now you can always convert CSP into a SAT with only a polynomial increase. Okay, everybody knows this much, that if you have a variable v with values 1, 2, and 3, then you now have propositions. V is 1, V is 2, V is 3. Those are the 3 propositions. Okay, but don't forget to add constraint saying only one of those variables can be true. If you don't, then you will find it the hard way. Right? So essentially, there's an all different constraint on top of V1, V2, V3. I'm sorry, not all different constraints. Only one of them is true. It cannot be all different. They're only true false. So that means basically you have to write a whole bunch of mutual exclusion constraint saying either V1 is not true, either V1 is true or, either V1 is not true or V2 is not true. Either V2 is not true or V3 is not true. Either V3 is not true or V1 is not true. If you write that, at least you made sure no 2 people have the same value. Both of them cannot be true. So actually, I'm not sure whether I'm writing it right. English wise, what I'm saying is you want only one of those values to be true. That's basically what I want. Okay? That should be written as a constraint. Okay. The CSP algorithms, this is one important obvious difference between CSP and SAT. The other is that CSP algorithms are written assuming that the constraints are procedures. They essentially call the constraints and say, are you happy with my partial assignment? Okay, what that means is that they have, whatever things they do, they have to do it in terms of these calls. But on the other hand, it also means that they don't need to write the constraints down in any declarative fashion. So they don't take that much space in some cases. SAT algorithms, on the other hand, are written on assuming clauses as declaratively represented. Okay. Now, the third bullet I forgot to mention is the practitioners of CSP versus SAT. Okay. SAT guys, remember SAT guys have even more constraint problem. They're only going to have Boolean variables and declaratively specified constraints. Right? Okay. And it turns out they are like the eager viewers of the CSP community. There is a SAT competition every other year. It used to be every year. And they keep improving the speed of SAT solvers every year. And there is a SAT conference where they talk about the best approaches for solving large SAT problems. You know what are large SAT problems? You have hundreds of thousands of variables and millions of clauses. I'll show you some little examples, but essentially on the 40,755th page, there still will be constraints if you write them down. Nobody ever writes them down, thankfully. Okay, they are talking about really, really large SAT problems. It's, anybody can solve 5 variable or 15 constraint problem. Okay, but then just because of that, everybody compiles their problem into this guy's problem. And remember, every time you compile, there's normally an increase. And all you're hoping is its polynomial increase. But if your planning problem is already 1,000 variables and you convert it into CSP problems, it becomes like 15,000 variables. And I say I can solve 5 variable CSP problems very fast. It's no good. Okay, and it turns out that SAT of all the people in this area, the most eager in developing new algorithms. It's just a community thing. Okay? I mean, why should they be that way? I don't know. Why should French have more fun and Americans have no holidays? I don't know. It's just culture. Okay? SAT has this culture. Okay? And so what happens is, whereas CSP guys come up with algorithms, talk about great properties of them, and then expect that some grad student will implement them. And the grad students will prove more theorems and expect that some other grad students will implement them. Okay? And so there are not as many. There are algorithms being developed for CSP, but nowhere near. They're not keeping up with the rapid advances in the SAT solvers. So despite whatever I said to you, you may be better off converting your problem into SAT than into CSP. Understand the theory of CSP, but convert it into SAT. You can convert your problem first to CSP, then to SAT, and it will increase both sides, and still you may solve it faster than waiting for the CSP guys to solve it. Or, actually you writing an algorithm to solve the problem yourself. Okay? Then comes the next one. In fact, the elephant in the room, which only one guy recognizes and probably the rest of you don't, is integer programming and linear programming. Because those guys solve exactly this class, not exactly, but enough similar problems. Okay? So I'm going to then caricature them to you too. So as far as he's concerned, I'm caricaturing them. As far as you are concerned, I'm giving you received wisdom. Okay? Anyway, so CSP SAT are connected to this problem, basically integer and linear programming problems. Okay? In particular, actually, a linear programming problem, let me just go here. So a linear programming problem is all of you know about linear programming, by the way, because when you were in high school, you've been made to, I know that my son had to do it, so I'm sure you had done it too. You had to write the linear constraints and you had to make the polytope and then find the corners and then check where the objective is the highest, which corner of the objective is the highest. So basically, a linear programming problem basically says maximize, let's say, 3x plus 4y. These are still has variables. Now these are continuous variables. Okay, these are real valued variables. Okay, maximize 3x plus 4y subject to the constraints x minus y greater than 4 and 2x plus 3y less than or equal to 0. Something like that. Okay, now it turns out that these constraints will define a polytope. This is basically only two variables, so it will define a two-dimensional polygon. If the polygon has area, that means it's not degenerate, then you know at least the constraints are actually satisfied. That they are satisfiable. The only question is, that means there are infinite possible values for x and y, which fall in this area of this polygon, which will all satisfy the constraints. The question, of course, is which of those values will make 3x plus 4y have the highest value? Okay, and the great theory from, this is actually easy enough to see for you here too, but one of the nice properties is the optimal always exists at a corner of the polygon. And the way to think about it is, here basically 3x plus 4y is a line. It just didn't tell you equal to what. So it's a set of parallel lines. So you start this parallel line and it keeps going up. As it keeps going up, it has a higher and higher constraint. Now the question is, before the entire line goes out of the feasible region, the last point, it still touches the feasible region, is what you are interested in. Right? And since these basically would have to touch one of the corners. Which corner, you don't know. That's the interesting part. Okay? But it's going to be only one of the corners. And the algorithm, simplex algorithm essentially, was one of the old algorithms, but it's considered the world's greatest algorithm because it essentially supports the entire industries. Okay? And George Danzig basically came up with this simplex algorithm, which has a nice way of going over the corners. And then later on, people actually, it turns out that actually simplex algorithm is exponential time, probably exponential. And for the longest time, people did not know whether linear programming is NP-complete or polynomial. Because the only problem they knew, only good solution they knew was essentially exponential time. But knowing the solution is not the way you decide complexity. Right? So for the longest time, it was kind of an open issue, and then people started finding essentially polynomial time algorithms for LP. Okay? And that's one way you prove that it's polynomial time. Here is an algorithm that's polynomial. It's probably correct, so it must be polynomial time problem. And those are called the interior point algorithms. Rather than go from corner to corner to corner, they start in the middle and go towards the right corner. That's basically what happens. Of course, there's a huge amount of actual details and that's what they want to do. Okay. There are several people who did this. I think the one that got a lot of press when I used to be in grad school was this Karmarkar's interior point algorithm, which basically made the problem polynomial. What's interesting is for the longest time, simplex will still be, even when there were polynomial time algorithms known and written up in SIAM journals, it would still be the case that simplex is what everybody would use because this known exponential time algorithm was faster in practice than the known polynomial time algorithms which had humongous constants. Okay, but my understanding is that interior point algorithms do have now, at least they have their sphere of applicability. So in practice too, they can be used quite well. But simplex hasn't gone away. Okay, so that's all about LP. Now the question is LP harder or easier than CSV? I just said everything to you. On one hand, it's harder because, man, it looks like you have to draw polytopes and then look for, the cardinal points, etc. But computationally, it's an easier problem. It's actually cute. It happens many a time. The continuous analogs of discrete problems are often actually cheaper, easier to solve. What makes LP hard is to just convert it into a discrete version, believe it or not. And the discrete version of the LP problem basically says, well, this is all fine, except I want y to be integers, because maybe y is the number of pilots. This is the airline, airline is trying to optimize its profit, and some random bunch of constraints about the fuel level, the number of pilots, etc. You can get fuel level at any continuous quantity, but number of pilots seem to come in whole numbers, right? And so saying I have a really good app, solution for 3.78 number of pilots is not going to help. Okay, now I say 3.78, that's kind of close to either 4 on one side or 2 on the other side, 3 on the other side. Maybe those 2 would be the optimal solutions. No, that's not true. It turns out that if you're only looking for integer values of pilots, the best solution may not have be 3 pilots or 4 pilots, but maybe 13 pilots. And the only way you can tell is actually go through all the actual possible assignments and see which of them is best. That is the integer programming problem. So the normal pure integer programming is where all variables are integers. And pure integer programming corresponds the best to CSP problems. And in particular, there is a kind of pure integer programming called 0-1 integer programming problem. And the 0-1 integer programming problem corresponds directly to the SAT problem. Now what's interesting culturally, scientific culturally, is work on linear programming, integer programming developed in operations research communities. Work on CSP got done in AI and combinatorial research communities. They won't talk to each other. And it turns out there are beautiful connections. So for example, one of the things that we see is one way of solving integer programming problems is to get bounds on them. And one way you get the bound is you basically relax the constraints. You remember, heuristics are always about relaxing constraints. If you relax the integrality constraint, then they become continuous. Then you get an LP. You can solve LP polynomial time. And the value of LP will then be, if it's a maximization problem, then the value of LP would be the upper bound for the actual integer programming problem. And really the way, one pretty reasonable way of solving integer programming problem is to do something like what we will see CSPs, which is give values to certain variables, then you have sub-problems, then you can establish their upper bounds, and then you do branch and bound search. Okay, so the SAT connects, so that 0-1 integer programming is SAT, and normal integer programming has direct connections to CSP. And so then the question then would be, I should have a slide like this, even though I don't right now, I can do it next time, as to what are the relative advantages of taking your problem and writing it as an IP problem as against a CSP problem. Now, if any one of them always wins, then there won't be a community called the losing community. Right? And the reality is neither of them win. There are interesting connections between when the IP view works better than SAT view, and the SAT view works better than CSP view, and so on. Okay? And there is actually an annual, 2 annual conferences called, one conference called CP, Constraint Programming Conference, where people from CSP, SAT, and OR go there. And there is another called CP-AI-OR, another conference. As if CP is not obvious enough, they have the CP-AI-OR, and people from exactly all these 3 areas go there. And there are textbooks written, especially by the guy called John Hooker, who is a well-known guy in operations research. He spent his essentially research career trying to make the connections between all the ideas that came in the IP side and all the ideas that came in the CSP side. And he has basically made his career on the IP side. So it would have been very useful for him to say IP wins, CSP loses, right? But after 2 books, he still can't say that they both have advantages and disadvantages. One last thing I want to tell you, the relative level of laziness. Remember, between CSP and SAT, I said CSP people come up with new algorithms, but then expect that may not be really implementing it themselves. SAT people are eagerly coming up with new algorithms and implementing them. There is no actual SAT industry. And this is for my caricature in IP, as far as I can tell, and I spent some time on this area, they leave it to companies. Okay, there is Cplex, there is iLog. iLog, this company makes Cplex. Okay, so they don't even bother actually coming up with new IP algorithms. There are few people who still write papers on that. Most of the work in operations research community is take somebody's problem, write it as IP, give it to Cplex server. So there is this great quote by somebody that industrial engineering and OR people develop graduate students who then go take somebody's problem and convert it to something else and give it to somebody else, so they have a job. AI people develop graduate students who automate everything and are surprised that they have no job. Right? But it's an interesting point to keep in mind that pretty much every idea that we'll talk about when we come back next time in terms of CSP have direct connections to IP. And many of them have actually been just looked at in the earlier parts, and SAT solvers are improving every year, but nobody does that for IP. Essentially, we leave it to iLog to do it. And iLog basically charges $1,000 for student license for Cplex, and then you do that. That's it. Okay. So there is also a scientific culture aspect of it between CSP and SAT and IP. I will come back next week. Thanks.